Hello, my name is Linus Rosenqvist and this is my first ever tutorial in Houdini. What I will be doing is to create a pop solver from scratch with just VEX code and nothing else. We will do the basic things. We will do sourcing first, of course, to add particles, and then we will give them some kind of initial velocity and other attributes that needed. Then we will also have a force that is added each frame, and we will of course then move the particles, and we will have collision with the ground plane, and we will also have some kind of internal collisions where we use an elastic collision algorithm, which is very basic thing, but it will at least give us a little bit of something. It will give us some kind of collision, although not very physically accurate and such. And a bit of disclaimer: this will not look super cool, and it won't be something you just take. This is easily recreated with a pop solver and a lot better and faster. But the point here is rather to learn how to build these kind of things in VEX, and that knowledge you can then take and apply to a regular pop solver, a flip solver, or agents, or rigid bodies, whatever that's pack prims, whatever that's like, yeah, whatever you want, basically. This will be kind of a beginner thing, but there are some intermediate things. So, I mean, if you haven't looked at Houdini at all, maybe this is not the first thing you should do. But yeah, hopefully you will get something out of it anyway, and same thing for people that are more advanced. So yeah, let's just get started. We start by doing a geonode and jumping right in. So what the first thing we're going to do is just drop down a solver, because we will do everything within the solver. So yes, it can be called solver, it doesn't really matter. So the first thing we do is drop down a wrangle. And this wrangle will be for sourcing, so we just rename it sourcing. I can't smell this is not going very well. So we plug that in from the first input, and this input is just giving us the last frame's information. So this first one will just run over detail, because we want it to just run once. This will of course force us to write to each point that we want to write something to. We can't just write attributes here directly, because that will just end up on the detail for the whole thing, not for each point. But we will just have to adjust to that. So the first thing we will do is we're gonna start with giving us some variables. The first one will be radius, which is the radius in which the particles will spawn. I feel that I'm kind of bad at typing and talking at the same time, so I write a little bit errors, but yeah, you will just have to deal with that. Source radius, what that be called. So what this HFS is doing is it just gives us a channel down here where we can write in a value. So we can just give this a value of, let's say we do this quite big, so let's say we give it a value of 10. I think it's a bit easier to do it that way. The next thing we will do is that we are gonna have another channel, which is an integer. So we call it int particle amount, and we give that also a channel float. Oh, sorry, a channel integer, which will be. You see, I can't talk and write at the same time, because I tend to write stuff wrong, or I just can't talk really well. It's like this is something I should be able to do, but yeah, you learn. We just give this a value of like 5 or something to start off with, to have something. What we also will need is a vector which stores the information in where the particles are born. So we call that vector. See, I can't talk and write at the same time. Vector, we call it new p or new v. Sorry, we call it new pos. And we also will have a velocity, so we do a vector for that, which we call new v. There aren't any old velocity or position, but yeah, I guess that's And we will also need something to identify the particles with, an ID attribute, so to speak. And the way we will do that is that we will, for each time this loops, we will get a bit more to that when we come to the loop. Each time this loop, a value will be added to a global attribute, which will be called temp ID. So the temp ID will store a global value on how far we gotten on our IDs. So each time a particle is born, we will add to this. So for each frame, we will add particle amount that we have. So let's see if I spell that apparently. So we do like that, particle amount, yes. So for each frame, this will add up. So we can actually see this right now. We have a solver, and what that is giving us is just giving us a detail attribute that just counts up 555. But you see, right now it starts as 5, which is not what we want. We want to start at 0. So what we need to do is we need to take this particle amount and give it to an ID attribute, which will then hold the temporary ID attribute, or it's not that temporary actually, but yeah, and we subtract the particle amount, and we also subtract 1. That will give us 0 to start with, and then it goes to, I mean, when here it says 5, it will subtract 5, but that gives us 0. I don't need to do that, sorry. Can I just do it like that? It should, yeah, it should work. No, we need -1 in the end. So right now it's -1, but then we add 1 for each iteration, and therefore the first one will be 0. Yeah, a bit complex now, we'll get to it later. So what we do now is we do a for loop for each particle here. So we do that with the for function, and there we need to specify the iteration variable, which is just called I here. And we also need to say how long this will run, and that is as long as I is less than the particle amount. And we also need to say what it does every time it's run through the loop, and that is just adding 1 to the I. So next iteration will have a higher number. Yes. So there is a loop, and that is not working at the moment. Int I will have to have a variable on that as well, so it needs to be start at 0. So there we go. And what we're going to do now is we're going to give ourselves some random position for the particles that we're born at. And the way we're going to do that is we're going to do it a little bit longer than it has to. We could do this with a sample uniform sphere or similar things to that, but we're going to do something that explains a little better. So what we're going to do is we're going to give each axis a random number. So I will explain this a little bit more later. So we start with doing a random for x, which equals to a random function. And that random function needs to use the iteration, and that iteration starts off with 0, so we should have, it starts off with 0, so we should add to that, else that thing will return 0, which is not good. So this we need to put in parentheses, and we're then going to multiply that with the frame, which just gives us the frame number. And the frame starts as 1, so we don't need to add anything to that, but we need to multiply that as well with something. And there we go. There we have a random value for the x on each frame and each iteration. So we just copy that and add that for y and z as well. Y and z. And we just need to change the numbers here so we don't get the same result. Yeah, that doesn't seem very random, but yeah, let's do like that. And then we change this as well. And I hope this will get us random stuff enough. It's usually, when you find there's something inconsistent, it usually is these things that fuck up. So what we have now is 3 variables, and we just store them in a vector. So we do a vector which is called random pos, and that equals to set, which just lets us specify the different let's say channels in a vector, or what do you call it? Different yeah, like what the fuck is it called? I don't know what it's called. Doesn't really matter. We specify the x, y, and z of the vector basically. So we just add our random of the free ones there, and so right now we have a vector which is basically just gives us. I just showed this in 2 axes, but what we get now is we get a random point for each iteration, which could be pretty much all over this little thing here. So positive y, positive z. This is of course a 3 axes, but here our points, our vector will end up at the moment. So I just Ctrl Z here. So what we need to do is we need to stretch this so it goes from down here as well, and around here as well, and around here as well. So what we need to do is just stretch it down so it can be +1 to -1 rather than just from 0 to 1 as it is right now. So yes, this is not a very efficient way to do it. Let's just move that layer instead. So to do that, we will just use a function called fit 0, 1, which takes a value from 0 to 1 and scales it to whatever we set it to scale it to. So let's do this. We say random pos, and you could of course do this whole thing in one function, but I think it's easier if you're not very familiar with the Vex to read it this way. Hopefully I'm right. Hopefully I'm just not making it harder for you guys. So we take a fit 0, 1, and that needs to know what value we are fitting, and that's random pos. And what we're fitting it to is to -1 and +1. So then we now have values all over. I'm not going to bring up my comp. We have values all over this place now, out here. But what we want is to have more of a spherical. Right now we have a square because it goes from 0, it goes all the way out. So what we want to do is rather to have something that looks like this kind of thing. So it's more a spherical thing. It doesn't look spherical because I can draw, but you get the point. So to do that, we start by normalizing this function, this value as well. So random pos equals to normalize random pos. And like I said, this is a not very efficient way of doing this, but I think it's easy to follow along if you get each step. So what we get now is that it says that the value of these, the x, y, and z axis should always be 1 combined. So therefore something that is, therefore something that is here will get stretched out, so it's there. And something that's here will get stretched out, so it's here. Here will stretch out here. And that gives us a uniform circle that is not a circle because I can't draw with the mouse, but you get the point. And that's good, but what we want is to have things all within this circle. So we need to give these, so it's not stretched the entire way, and we can easily do that by just giving this amplitude. So if they are out, let me see, if they are out here, then we get a random value which says how far on this line they gotten. So maybe one gets there, and maybe one is out here, and it gets moved back there, etc., etc. So to do that, we have to do another variable, which we call amplitude. So we do float amplitude equals to we should get like a random thing here. So we do a random function again. And we want that to be random for each point and each iteration. So we do iteration plus 51, and we multiply that by our frame, and we can then multiply that with something as well. So there we go. So that will give us a random value for each iteration and each frame, which is good. I wonder if there's something else. No, this will get random, I think, right? Because that doesn't. Yeah, I think so at least. No, we probably should actually, maybe we should multiply this as well. Let's do that actually. We need to do like this. We put that in parentheses as well. And yeah, I think that's good enough. So we do that before we do the multiplication, else it would be, yeah. I think that's good. We'll see if there's any problem with it. So now we can say that our position where we want the points to be born, which we will call new pos. We have it up here, you see. So we'll say now that new pos equals to random pos multiplied by amplitude. And then we get the value within the uniform circle. And then we have our position place. So now we can actually, what we could do is we could just create our points if we want to. So to do that we do it very simply. What we do is, first of all, is we create an integer which will store the point number of the created point. So we call that new pt, and that equals to add point, and then we say what geometry string, which is 0, and then we just say new pos. So there we go. And what we should get now is points, and those points should be within a circle. Let's see if that works. Let's just see if we bring this up. Yeah, those are inside a circle. And let's see if we scale down the radius. We can do 50 points or something. Scale down the radius. Oh, did I forgot to add to the radius? Sorry, we forgot the radius, I think. Yeah, random pos times amplitude and multiplied with the radius, of course, which is just radius. There we go. And now if we change the radius, you will see that we have something that's going upward. So that's good. What we could do now, we could also name things here. So just write create points or something. Create points, and we will say up here that the loop is starting. And we should, of course, actually move. Fuck it, we keep it like this. So then we're gonna create our ID, which we have already started with. And what we do basically then is just create ID, and what we can do here is we can just do ID plus equals to 1, because we're starting at -1, so that will give us the first ID to be 0, and then we store that. And now we have a point number, so we know where to store it. So we say set point attribute 0, which is geometry string, ID, which is the name of the variable, and then we need a point number, and that will be new pt, since we created that variable up here, and that stores our point number. And then we just say what we want to store, and that is ID. So let's see if this works. Maybe we should step back in order to get it right. Yeah, here we go. So what's going now is the creating points, and those points get an ID. You can see it goes from, yeah, we have values, that's correct as well. Good. We have a little tendency to have more things in the middle, and we just, yeah, we don't care about it. I'm not sure why that is though, but I guess there, no, maybe not, maybe just wait. No, it's not just the way it seems, I think. It seems like there are more in the middle. And I'm not sure why. Maybe there isn't if you move around. Well, are there more? Maybe it's just a... No, I don't think. Maybe it's just a thing that it looks like that. I'm not sure. Well, anyway, that's that. Then we need to create some more attributes. So in order to do collisions, we will need to create density, and we also need to create p-scale. So let's do that. We just call it create density and p-scale. And what we do is we do density. We need to spell this correctly, otherwise we'll be density equals to channel float density. We just keep this as a constant right now. Maybe we change that later, but for the sake of it, it doesn't really matter at the moment. And we also create a p-scale. And the p-scale, we want to have a distribution that's not just uniform. So in order to do that, we just start with creating a p-scale attribute, and we say that's equal to random, and we can do that from ID now, because ID is completely random, so that's good. We don't need to use the more complex things. So ID we get as a random number for each ID, and since they are unique, that should work. And then we just put that p-scale within a ramp. So we say p-scale equals to shramp, and we name that ramp something, call it p-scale ramp, and we say that the variable that you use is p-scale. So that gives us a little ramp. That ramp we can then specify how small the smallest will be and how big the biggest will be, and like give it like a distribution that maybe looks something like this. I don't know, many smalls, a few big ones usually looks better, I think. We could of course also do another interpolation here, but yeah, it doesn't really matter. But we will also want to have something that just sets the scale of the p-scale, because right now it's just between 0 and 1. So let's do that as well. So we do another line here, which is p-scale equals to actually multiplied equals to, which just says it should be multiplied. I don't need to write it twice. And we just do another channel, which is p-scale mult. There we go. And then we just need to store these attributes. So we can do this the same way we did up here. So we just copy that one, and we store p-scale, and we store it in. So we just say that we use the p-scale, and we use p-scale attribute, and we do the same thing with density, and we store density attribute. There we go. And since this is all within the same loop, we just use the new PT thing here. Next thing is velocity. So let's say that we do that. Create velocity. Let's call it vel for short, although that's a bit confusing because that's what you're doing within fields. So we need to have an initial velocity, which we could just direct in whatever direction we want. And that should be, we have that created already actually there. I don't know why I created that up there, that might be a little bit confusing, but yeah, we created a new vector here called flow vector, vector new v. So we can use new v here, down here. So create velocity. We just say new v equals to channel v, which is a vector channel, and we call that initial velocity, like that. And then we could also, add some noise to that. Should we do that? Yeah, let's do that. So let's say that we want to randomize that a little bit. So we do a float, which we call random init v for short, better. And we say we create a channel for that as well. So we say channel float random init v in English, not v in Swedish. And then we just give that a random value. So we do float random v, and we say that should be random, and we just take ID and we give it another seed, something like that. So that gives us a value between 1 and 0. And then we could just do a vector which stores the randomized velocity within one. So I'll show you. So we do vector. This is kind of the name, get a little bit similar here. We call that randomized v then maybe, and we say that equal to new v multiplied by random v. This is a good reason to use the lerp function as well, I guess. And then we could interpolate between these. So the more of this random initial velocity we have, the more we will use the randomized velocity, and the less we have, we just use the constant solid thing. So let's do that then. We say new v equals to lerp, which will interpolate between these two, and we say new v as the first one, and then we say randomized. I'm going to copy this because I will misspell it otherwise. We say randomized v, and we'll do value we will use is random init v. Okay, this was a bit annoying, but there we go. And then yeah, we could just use our channel down here that we create now. So we can give it a initial velocity like 1. We can give it p-scalar 1. Doesn't really matter now. And then the random initial velocity. Let's set that. Let's check the spreadsheet here as we change that. So step back and see. No, we haven't stored it. We have to store it first. Let me just store it as well. So we use the set point attribute first here. So let's do that. And we store our v, and we use what's called new v. We could just call it v, I guess. So there we go. If we see here, we have a value of 1 on everyone, which was what we gave it. And we then give it random value, you will see that some get lower, actually everyone gets lower because it gets random. So we can give a little random. This is the little noise function that works in like 1D. Could of course do this more fancy as well, I guess. Could base it on position, etc. But now we just base it on ID. So there we go, and then maybe we should have a 3D noise to that as well, actually. So before we create that, we do create vel noise. I don't know why I'm doing underscore here, but yeah. Like I'm talking and I'm doing strange things. When I talk, I can't really write correctly at the same time, and yeah, so therefore either thing fucks up. But yeah, let's just do that then. So we start with we need some value variables here as well. And we're just gonna use channels for that as well. So we do channel frequency. Call it just frequency. I don't want to write long stuff all the time. So we do a channel vector, and we call that noise noise frequency, and we do a vector self-amplitude amp. We call that. No, we already have an amp, so we call it noise amp. Noise. You should of course be better with your variables than I am. Not just have kind of system for it. I guess would be better than just write random shit. And we call it noise amplitude. And then we could do a time offset as well. So let's do that also as a vector. Time offset. We do a channel vector. This will be a lot of channels, but yeah, it's good. Good to have these controls maybe. And then I'm just gonna multiply that with the. Yeah, let's do that. We just multiply that with frame. Or even better, we multiply it with frame divided by 25, because that's my frame rate. And I know it would be, you could do a channel frame rate there as well, I guess. And could also, of course, if you have substeps, we should as well take that into consideration. But I skip that now because it will be, I think this will be a bit long anyway. So we skip substeps now, I think, which will make our collision look kind of ugly. But yeah, it's fine. Or maybe they won't. I'm not sure. We'll see. So then we do a noise. So we do a noise function. Let's do x noise. And for that we will need the position, which is new pos. Okay. Okay, sorry, I don't know what I'm doing here. We need to name this variable, of course. Yeah, always something that you miss. So just call this vector noise, I guess. I forgot the equal thing here. And that should be, of course, be multiplied. Stupid frequency and plus offset. Time offset, sorry. Like that. And yeah, so that's good. What else? Yeah, there we have the noise at least. I got a little bit distracted from doing the strange thing here. So yeah, we're gonna offset that noise actually. So just let's create a vector again. We say vector offset, and that equals to. I'm gonna remove 0.5 in each axis. 0.5 minus 0.5 and minus 0.5. So now we have a noise between minus 0.5 and we have to plus 0.5. So then we just do noise plus equals to offset, and then we should multiply the whole thing with 2. So let's do that as well. We do this in a bit unnecessary steps. We could do this in a few steps, but yeah, so we do that, and then we also need to multiply it with the amplitude. Multiply equals to amp. So there we go. A few steps unnecessary, and then we add that to the new velocity. So let's say new v plus equals to noise, and now we're storing the v. So let's just see if that works. Here we go. We have our. That seems to be working, although of course like that, and then let's just see what happens if we add to the noise amplitude. Nothing happens. Why is that? That's because we're in that, but okay, maybe it's working. Let's bring up the frequency to. If we have frequency 0, of course it doesn't work, but if we bring it up, but then the amplitude doesn't seem to be changing a lot. So I guess we didn't get the amp. Yeah, because we take amp, sorry, we need to have noise amp here, of course. There we go. And now we can change the amplitude of change the frequency, and we can change the amplitude. More amplitude, higher things, and we can also, of course. So that seems to be working if we look at it here, not if we look within the solver. We could, of course, just freeze it here so we can see things directly. Yeah. So frequency all over the 3 axis. And let's put that to 1. Let's see here. The -1 there. Okay, this seems a bit off. It's so correct, I guess. It's just that we get a lot of upwards and downwards, etc. So that's good. We have a noise thing, and we can step up from the solver and see how this looks with the p-scale. So let's do a copy to points. Sphere. Just copy a sphere to this, and we will see how it looks. And it's super big, of course. So it's going to bring down the p-scale. Bring up the density to 1 as well, so we have something. Bring this down to 5 particles, because that's more reasonable. And we bring down the p-scale multiply to 0.1. Okay, so Houdini crashed for me, so I just gonna, yeah, I don't know, I might change the little variables, I think, and I meant back to say, but I think we are pretty much where we were. So right now this is working, and if we play it, it stores a lot of things here, as you can see. And there might be a problem with when it stores a couple of frames, they start intersecting. So I'm just gonna see if we can remove those intersections so we don't get a problem further down with those, because they might be a little bit of a problem for our collisions. So we're just gonna remove those. Let's go remove intersection, and we're just gonna say, what we're gonna do is that we're gonna check for near points, and we do that with a function called near point. We call it near pt, and that should just be the function near point. And the near point just needs, I think it just needs the geometry string, right? No, it needs position, of course, as well. That's new pos. So let's see what's happening. We're just gonna store that attribute to see what's going on. So we put this thing here, and we just store it. Sorry, we shouldn't bring that up. We should just store it, and we store near pt. So that we store the point number. So yeah, that seems to be working. We get a near pt for most of those. Just see what happens if we run. Yeah, so it works. It does, of course, not check on the just birth things, but that's fine, because it won't intersect in there anyway. So there we go. Now I have a near pt. We can remove this again. I just want to check that it worked. So then we need to look at the p-scale and position of that point. So let's do that. We do a float, and we call it p-scale 2, which equals to point, and we should look at the p-scale of our near point, near pt, and we should also look at the position. So we say vector, we call it p2, and that should be equal to 0, the position of the near point. So now we have that stored as well. Now we can just look at the distance. So we can say if distance, and the distance should be the distance between new pos and position 2. If that's smaller than our p-scale plus p-scale 2, and we can multiply that with like 2 or something to get a little bit more, a little bit bigger things. And if that's true, then remove point and just 0 new pt, which is our point number. But we also need to say, actually, we also need another variable here, which is if it finds something first. So we say if near pt is not equal to -1, I think that will work, right? If it's not equal to -1, so not 1, but -1, then do this thing, because it won't. So let's see if that works. What's happening now is that we get a lot of points. So it births the points, and then it stops birthing points that are within that, so we don't get that error. Maybe 2 was a bit too much here, so let's not do that. Let's do like 1.2, so we have a little bit of margin, but not that much. So basically it's sourcing particles and it's packing them, but they're not intersecting, as you can see. Good. Yeah, so that's, I think, is pretty much it for the sourcing part. Now we have particles, and we have a velocity, and we have p-scale, we have ID, and we have a density, which is what we pretty much need now. So yeah, let's move on. Okay, so before we move on, I just saw some things I missed here on the sourcing. So I'm just going to correct these first. And the first thing is that we forgot to store our velocity. So right now we create the velocity, but we are not storing it on the points. So that's an easy fix. So we have store velocity there, and just gotta do a set point attribute again. So we're gonna store call this v for velocity, and what we're gonna store is on the new pt as always, and what we're gonna store is the new v, which is the new velocity. So basically that's that, and we're gonna move back, and we're just gonna see that we have velocity. Yes, so we have the velocity, that's good. And also I'm going to store the rest position for the particles, which might be good to have as well. So rest position is basically their birth position, which can be of use later on. So we're going to add, say that we store rest there as well. So we're just going to copy one of these set point attributes, and what we're going to store there is the rest, and we're going to use our position for that. So we just take new pos and store it as rest. If that changed later on, that would be useful. So if we step back and look, we see that we have a rest here. That's correct. That's the same as our position. Good. So when that's done, we could move on. I'm also going to change the values down here a little bit because I think we're a bit off. So I'm just going to do source radius of 30, particle amount of 3, and I can keep this as it is. I'm going to do a lot bigger p-scale for us to see, and I'm just going to give it a national velocity of one direction rather, and the rest we can keep as it is. So yeah, let's move on. So later we're going to do another source as well, but I think we start with, let's see here, yeah, see it's super big now, but that's fine. See the sourcing is working as well. Later we're going to do another source as well in order to try out the collisions, but right now we're going to move on to force. So we do another wrangle, and we call this compute force. And basically what we're going to do here is give them something that's added each frame. So first we're going to create, first we're going to actually take down the force to 0 because we want it calculated each frame. I don't think it's super necessary to do that for be sure that we don't have any problem. What we're going to do is we're going to give us some kind of wind. So we're going to do a vector called wind, which we say equals to a vector channel called wind, and we're going to give ourselves some gravity. So we're just going to do a vector gravity. We're going to equal that to a channel vector as well. Call that gravity. Like I said, I can't really talk and write at the same time, so I tend to write strange things. And we're also going to have a noise vector. So just initiate that. So the first thing we do is we create the noise. The first thing we will have our other channels as well, of course. For that, we will need a frequency. So we do a vector freq, and that should be equal to a channel vector as well. We call that noise frequency. And then we'll also do amplitude. And we'll also do this as a vector, so we can change the amplitude for different directions. So we do channel vector as well and call it noise amplitude, noise amp. We're going to do a time offset as well, also a vector. And that is something that moves, so it moves along with time. And that should be a channel vector and call that time offset. And that should be multiplied by maybe frame, and we divide that by 25 or something like that, so we don't get too much. Could do time there as well, but I don't want it to start at 0, so yeah, therefore I do frame instead. And then we do we calculate the noise, and we do noise equals to, and we use the function xNoise here, which will give us a noise based on a vector, and we do that at position, and we multiply that with frequency, very standard procedure for so the higher the frequency, the lower the big, it kind of scales up the position, and therefore, but we still have it on added to the position, and therefore it kind of shrinks. I don't know if that makes sense. It's same thing as in BOPs, and if you know noise functions, you understand what's happening. Otherwise, I should explain, but I feel like it will take too long. So we do like that, and that gives us a voice between 1 and 0, which is good, but we want it between -1 and +1. So we're going to do we're going to create a vector which we call offset. This could be done in different ways, but I think it's a bit clearer if I do it like this. So it's going to say that's equal to -0.5, -0.5, and -0.5. And then we do this in a couple of steps. So we do noise plus equals to offset, and then we do that. Then we have a value between -0.5 and +0.5. And so then we can just multiply this by 2, and we get a value between -0 and +0. And then, of course, we need amplitude as well. So after this is done, we can just do multiplied equals to noise amplitude. Noise. No, we just call it amp, sorry. Like that. So let's see if this works. And yeah, then of course we're gonna store the wind and the gravity as well. So we can do v at force, which is a global variable, equals to wind plus gravity plus noise. So noise is kind of a turbulence thing. We're just gonna get some very low values here because this is calculated a lot. So we're just gonna give it so it shrinks down a little bit, minus, I don't know, 0.45 maybe. The frequency should be quite low as well because we are on a really big scale now. And then the amplitude, we can do something like, I don't know, something like that. And time offset, this is how much it moves with time. So we do 0.2 or something like that. There we go. There we have the noise computed, I thought, but we have an error. Let's see where there is vector time offset. We've got this one there. Anything else? No, seems to be working. Yeah. So we can just look at our points. No, can't. Yeah, we can. There we go. We have our points. We can just look at your spreadsheet, and we have some kind of noise. We could just see what happens if we do bring up the amplitude. It works. So that's good. We could of course also try what happens if we give it wind. Yeah, so it seems to be working. So gravity and wind you could do as one thing. Now I had wind 0, but it might be good to be able to add wind later on. Yeah, and when that's done, we should move the particles. So we do a new wrangle, and we will say update vel move. And while we're doing this, I'm going to start up Photoshop because there are some things I want to show later on, so we'll start it up. So we don't have to wait for that. Or of course I could pause the video, but I'm too lazy to do that. So then I have to edit and stuff, which I will have to do anyway because it's crashed for me and stuff went wrong. But yeah, so what we do now is that we add a drag force. So we multiply a vector, which is basically just subtracting from it. So this will be at maximum 1 and at lowest 0. So we do 1 minus a channel float, which we call drag force, like that. And then we do v at v plus equals force. So we add in our force to velocity. then we do v at pprev, which is a new variable we declare, which is the previous position. We store our position there before we then move it with the velocity. So basically what we're doing is we take our velocity and we drag it down a little bit. Maybe we should do it last, but it doesn't really matter. After that we add the force, we store our previous position, and we move our new position. And if this is correct, we should have something moving here. So let's see. Here we do. And it's super fast, so yeah, but let's do it slowly. Here we can see we have our particles moving with the velocity. So that's all good. Yeah, good. It went up here. We're just going to bring that up so we can look at that later. That's my explanation for collisions, which I still can't draw, but you will still have to look at it, ugly as it is. So yeah, let's move on. What we need to do now is we need to see if there are collisions and calculate those. And this is a bit complex, at least more complex than what we did previously. So what we are doing is something called elastic collisions, which you can find on Wikipedia, which is basically this, points that don't lose energy when they collide. So there are a lot of explanations for this, and you're very welcome to read it. I haven't, but yeah. So I just stole something here I found, which is two-dimensional collisions with two moving objects, and we're using the formula down here. So basically what this is saying, we could rewrite this as Houdini code. Let's see if we can do that very easily, so you get a little bit more understanding of it. Or maybe you understand math better than I, so you don't need this. But I'm just going to bring up my note. Let's bring up, yeah, we do it in Notepad, why not? So basically what we're saying here is V1 equals to V1 minus 2, this is the mass of the second particle, the one we're colliding with, that 2 times divided by the combination of the mass, and then that's multiplied by the dot product of velocity 1 and velocity 2, which is our main particle and colliding particle, and the position 1 and position 2. And basically what that gives us is an angle. So the dot product is, I could try to show you, bring up another thing, turn this off because this is not relevant. So basically, where am I here? Okay, I'm just far off here, I think, or zoomed in or something. I'm not sure what's going on here. Okay, there I am. Good. Sorry. Let's just zoom in and remove that. Bring up a new layer. Just turn those off, and yeah, let's just do another layer here. And here, what we're doing basically is that we look at dot product. We have two vectors. So this is vector A. Let's say that, I can't still not draw. This is vector A. It's pointing that direction, and this is vector B, so to speak. And the dot product basically gives us this angle. So if these are on the same, if they're pointing in the same direction, it gives us a value 0. And then in the one direction, the further down there, it goes to, I don't know, either +1 or -1. In the other direction, it goes in the other way. So let's say that, I don't know if this is wrong, but we say it's -1 if you get all the way back here, and it's +1 if you get all the way back here. So what we're doing is that we're looking at the difference between the first velocity and the second velocity. That's our first line, first vector, so to speak. And then we look at the position difference, and that's the second. And then we look at the angle between those. Yeah. And then that's divided by the distance of the position vectors squared, and the whole thing is multiplied by the first position vector minus the second position vector. So that sounds a bit complex, but it's not that complex. And if we're going to do this in Houdini terms, we could rewrite it, because we need to, so basically we can just say, so like velocity 1, which will be called V1. I don't know if I need to do this because it's very clear here. I think it's just changing the x to p, kind of. So I don't know if I need to rewrite it. We will write it in the code anyway, so I skip this, sorry. So basically what we're going to do is we first going to create a wrangle here to do the thing, and we just call this check collisions. Yeah, so what we need, first of all, we need to say that they haven't collided. So we need to create, that's like our first starting state is that they have not collided. So the point will have an integral collided, which is 0. After that, we need to check our points that is near and see if what values that have and where it is position-wise first off, and how big it is, and see if we have collided. So we're gonna do a near points function, and we're gonna call this near points, which is an array, and that array is basically just gonna say near points, and it's gonna check if we have some kind of collision, and we're gonna check our geometry in 0. Okay, I'm just gonna pause, sorry. Never mind. We're gonna check our position, and then we're gonna check in a radius, and that radius could be p-scale times something like 5. So we check in a radius that's a lot bigger than a p-scale, but since we have other particles that are bigger, it's good to have a bit of margin here. And this is just giving us the value, so we will calculate whether they are close enough or not later on. And then we need to check, we need to say what point we're looking at. And what we're doing now is that we are, the array basically takes, let's do a new layer here. So the array says this is our scale, it's kind of this big, and maybe it finds particles that are near, like 5 times this scale. So maybe it finds, let's call this 0.0, and this is 0.3, and this is 0.7, let's say. So what this near points does is stores an array where it stores all the points that's the closest. And the first one it stores is itself. So the first value of the array will be 0, which is this own point. And then it will store 7, because that's the second closest, and then we'll store 3, let's say that. So then this is the array. And what we need to do is look at the second one of these, because that's the nearest point that is not itself. So therefore we're declaring that as a new variable, which we call near point. PT, and we just say that that's the first, the second value of the array, the second input of the array, second, I don't know, point of the array. So we just say that it's near points and 1, which declares, because the first one is 0, so this is the second one. So that's good. And then we're gonna check if the near point, so we're just gonna see if there is anything, if this has given us anything. And here we kind of cheat, so we say if it's bigger than 0, then we start our thing here that's gonna happen. So this is like so if it doesn't find anything, it just skip this part. So then we need to take up all these things that we will need for collision. So we need a second mass, and we need a second velocity, and we need a second position. And the mass is calculated from the density and the p-scale. So we will need both density, p-scale, velocity, and position. So let's just do that. We say vector, we're just going to call these 2 of everything. So we call vector p2 for the position. And then we look at point, the geometry is 0, we look at position, and we look at our near pt all the time. So that's good. And then we can just copy this and do the same thing for velocity too. And then we look at v, so that's not harder than that. And then we can do the same thing with, it's going to say float here instead. It's going to float density 2, and we're going to look at density. And then we do the same, we're going to take this one instead. We just copy this one, and we call this p-scale 2. And that's p-scale of near pt. So that's good. So now we got the variables that we need, and now we're gonna see if they actually, just gonna call this declare variable, so get variables. Variable. I don't know, variable, how do you spell that? Variables, that's the way you spell it, I think, maybe not. And then we're gonna check collisions. Sorry, I'm bad at spelling, especially in English, sorry. Check collisions. And then we're gonna declare a new variable, which is, we call distance. Maybe distance collision, like how far is the other particle. And basically we just do distance between our position and the P2, which is our nearest particle. So that's one thing we will need. And we're also going to do a variable called p-scale sum, which is the combined p-scale of the 2 points. So that is then p-scale plus p-scale 2. And then we're going to do another if statement inside this if statement, and that's basically just if distance call is less than p-scale sum. And that's basically when we have collided. And then we're going to change the variable of collided to 1. And then we're also going to check how far into each other are they. So we're going to do a new variable again, which is called collision amount. And this will be needed in order to move it back so it's outside the collision. So we do p-scale sum minus distance collision. So that's just basically people just writing stuff here. So that's good. Now we know if they collided and we know how much they collided. So now we can calculate the mass, and that's needed for doing the correct collision. So like we see here, we need a mass divided by the other mass. And the thing is that the mass is basically the p-scale times the density, but since we are on a 3-dimensional plane, we need to have that by the power of 3. And then you should, in order to do this correctly, you should also multiply that by 4/3 of pi or something like that. But that's just a constant, so for us it doesn't matter because we're not working with real world things anyway. It's very far from something in the real world is. So we do mass and we do power of p-scale, multiplied by density, and then we just do that by the power of 3. And then we can do the same thing for our mass 2, because we need mass 2 as well. So that's the power of p-scale 2, density 2, and power 3. And we can also just create a variable called mass sum or something for them both combined, because we will need that for, it doesn't really matter, we could do that later on as well, but now we get an error. I don't know why, I have to check that. Where is the error? We can check later. I'm just gonna see, you see down here we have the both p-scales, we divide by both p-scales, so that's good. I don't know what's the error here. Okay, let me see, I don't know. Why don't I get a little message here? Okay, something is wrong. What's wrong? It's probably here somewhere, I guess. Float mass. Just gonna move this, see if it was here. Still error. Why do I get an error? Okay, this is very annoying. I hate when you don't get the tips for what's wrong. I'm just gonna do a quick check here. just remove everything. It's probably, yeah, it's probably just I forgot. I think I know. If, yeah, so annoying. Sorry. It's just we're missing a square bracket down here. So there we go. Now it's working. Sorry, I just like to check every once in a while because otherwise you have to go back and check it later on. So that's good. We have the sum of the mass, and now we can move on to do. This thing is easy, like the mass 2 times mass divided by that, so we don't have to do that right now. So we can instead move on to this dot product thing up here, which we're just going to call angle. So let's say that calculate angle. So basically what we do then is we do another float here called angle, and that should be the dot product of at v minus v2 and at p minus p2. Just like if we go back and check, you'll see that's what we're doing here. So that's that v1 minus v2 and p1 minus p2. So there we go, there we have the angle. And then we should calculate the next thing, which is this that we divided with, and we can call that distance. So that's position 1 minus position 2 squared, or rather the distance between. It's the same thing. It could be, you could do the length of those two, p1 minus p2, or you could do a distance of them combined. It will give us the same result. So we're going to do the easy solution here. Calculate distance. Calculate distance. I'm going to call it float distance, and that should be equal to, because this was squared, so we do power distance at p, p2, and we do that by the power of 2. I think that's correct, yes. Good. So now we have those things we need. So now we can calculate this whole thing that we're gonna then subtract from our velocity. So let's, and this is a vector. So we're gonna call that vector, let's see, we're just gonna use a little bit of clarification. What we do, we say calculate new vector angle, or something like that. So we do vector, and we call that correction. And that correction should then be, yeah, here's the thing. In this here, they start with the mass divided by that, and then they multiply that by the dot product and the distance, and this results in a float, and this results in a float, and this is a vector. And as you know, or might know, in Houdini, if you do this, you will get a float result. So we have to start with this, and since it's all multiplied, it doesn't really matter, you can change this around, moving back and forth. So we start with at position minus position 2, which is the last part. Then we multiply that by 2 times the mass 2 divided by the mass sum. And let's follow along here, and we can see, if we look at here, that's 2 times mass 2, which we see there, divided by mass sum, combination of 2 masses. That's correct. And then we multiply it by the angle, and then we divide it with the distance. So that's this part, angle divided by distance. And the distance we already squared, so yeah, we don't need to do it. And then we can do a new vector which we call new v, which is the new velocity. And that should be equals to v at v, and minus correction. So then we're doing this part. This is correction now, the whole thing here. This is the velocity one. So now we calculated it for this point. And the thing is, we run all points and calculate this before we move them. So therefore, we don't need to calculate it for the second particle. We will come to that in the loop when it continues anyway. Yeah. So basically what we have now is we have our new position, but what we need to do, like if we have our points, we have a point 1 here, which have p-scale of 1, and we have a point 2 here, that's a p-scale of 2. What we calculated was basically we're just looking at x-axis here, we can see that we have x-axis of 0, and for the first point we have x-axis of 2, which is here, and then for the second one we have 0. And we have a p-scale of 1 and 2, which is p-scale sum 3. So what we did was we basically said that the distance between these are 2, and the p-scale minus the distance is 1. That is the collision amount that we talked about. So that's what we call column amount. And what we need to do is we need to move them back so we're not at this point anymore. So if we were to move both by the collision amount, we would be off, of course. We would be farther apart. So what we need to do is take half of the collision amount, which is 0.0, and move our first point by that and our second point by that. I hope that makes a little bit of sense. And I'm sorry for being such a bad drawer. I can't help it. Or I could probably practice, but I really don't feel like doing that. So what we're gonna do then is we're just gonna see what direction they came from. So we're gonna say here move collider. We're not moving them actually, we're just calculating the movement. So first thing we need is we need the negative velocity in order to move them backwards. So let's say we call that negative v. That's equal to, and the thing is here as well, we don't need to know how fast they're going, because we already we just need the angle in order to move them back, because we know how much they collided, so how far what speed they came with doesn't really matter right now. We rather need to just have the direction. So to do that we just normalize it, and that gives us a unit square, whatever, a value of 1, so to speak. So that's just the direction. So we do normalize velocity, or normalize negative velocity, that is. And then we can basically just say that we can create a vector which we call p correction, which is a position correction. And that should be equal to negative v multiplied by the collision amount, and then, as we talked about, divided by 2, because we're doing this with 2 particles, we have to split the difference. But then again, we need to move it in the new direction, because we don't want to lose energy, or we don't want to lose speed. So if we just did this, then it will not travel as far the time it collided. So we need to take how far it collided in, and instead move it in a direction that is the new direction, so to speak. So what we're saying now is at the moment of collision, which is rather not here but here. Let me see. When they are colliding, we move them back now. So at this moment we instead need a new vector and travel the same amount as we collided in that direction instead. So we take our p correction again. I don't need to do the at there. I don't need to do the v at there, but I do it anyway because it's good practice, I think. And then we can just do plus equals to normalize again, and then we normalize the new v, which is the new direction we calculated, but that has a length as well, so we need to normalize it first. And then we multiply that as well with the call amount. And once again, we divide that by 2. So then we move in a correct new direction. And since I didn't do collider as a global variable, I think we just did, sorry, it's gonna check it. Yeah, I did a new integer for collider, which is kind of stupid, but yeah, I did that, so let's keep it that way. So just do I at collided equals to collided, which is of course 1 here because we have a if statement for it. And then we do v at new v equals to new v because we didn't. Did we do that? No, sorry. Here's something. We shouldn't do that. That's not a global variable. So v at new v equals to new v. Yes, and I think that's correct. Let's see. We also need to move them, of course, and that's super simple. So we have to do a new wrangle here as well, and say move collided. So if collided sorry, equals to 1, we need to check that of course first. V at v equals to v at new v, and p at v at p. You can do it to be serious. You don't need to do that, but yeah. Equals to add equals to p correction. Hopefully that will work. And that's it. So yeah, let's move back and play this, see what's happened. It's hard to tell and shit gets fucked up. So something is wrong here. What could be wrong? Let's see. It doesn't seem like it should be wrong, but no, it's not wrong. Sorry, it was something, yes. So it's hard to tell right now what's going on because they're not colliding. So in order to fix that, oh, we actually didn't even move the collider one. It wouldn't matter right here. Okay, now it's fucked things up. So there was something wrong. Yeah. So what was wrong was, sorry. What was wrong was basically we forgot to, yeah, we just called new here, vector new is equal to new v, and it should be equal new v. So a very basic mistake that was giving us all things was just stop when it collided. So this works, and we don't have any collisions, we shouldn't have any collisions, so it's hard to tell right now. So in order to try this and see if it works, we're just gonna do a new sourcing up here. So we have our first source, and we're just gonna basically copy this and call it sourcing 2 or something like that. And we need to change a few things here, not much, but in order to get this to work, we need to do some corrections here. So first thing we will do is we will move this. So when we do the new pos, we're just gonna move it to some new point. And yeah, so basically we have create point, new point, and we're gonna do vector offset, and we're gonna do that to a channel vector called offset. Why is it giving an error? Aha, we can't use offset position. We already have that. Look at that. And then we can do the new point should be new pos plus offset pos. And we also need, when we check the or we should actually not do like this. Sorry, we do like this. We have the new pos, and let's just say that, because if you're gonna work with the checking for intersections, we need to do like this instead. New pos plus equals to up here, offset pos. There we go. Then we can just do an offset position, and yeah, let's move that in some direction. Let's say like 610. Let's see if that works. And now we have, yeah, of course, and then we need to give it initial velocity that's different, of course, as well. So let's do like -7 there. I think that might be it. And now they are moving towards each other, and they kind of are colliding, and it kind of works. Yeah, so it's not super realistic, and it seems to be a little bit. Oh, it's just probably something that looked a bit off, but if we move in a little bit, we can see that it actually is decent. Yeah, it's hard to tell there. We could, of course, move out, and maybe we could just give these some kind of color based on, oh, maybe not, doesn't really matter. We could give them some kind of color based on their rest position, but I think we don't need to do that right now. So that's good. We could also give it the whole thing a ground plane or something like that in order to see things a little bit more clear. That would make it probably a bit easier to see the collisions here. So let's do that as well. Just say ground plane. And the thing is here, I can't talk about it. The thing that will happen, what the fuck's going on? My computer just froze. Okay, it works. We call this ground plane. Ground plane. And it's going to give it an infinite plane, so what we need to do is just do a vector that's called kind of ground or something, and do a channel vector called ground plane, and this will be infinite there. So then we can just check if our position, our y position, because it's just on the ground, minus our p-scale, minus p, that would work, right? Yeah, I think so. Minus p is less than ground dot y, so we are interested in y position. Then we can do v at v dot y equals to negative v at v dot y. So we just move it up instead of, if you're going down, you just move up. And then we also need to move it up so it's not below ground plane. So we do v at p dot y equals to ground dot y, and we also need to add a p scale, so we take that into account. And this should, p scale, yeah, I think this should work, right? Let's try it. We just add a ground plane, maybe like -45. So we have it far down. We are on a very big scale here. So yeah, that works. They're colliding. The thing is, it doesn't show up here, but if they get too close, or if they're forced by the ground plane to move into an intersect position, they will get stuck into each other, just rotate around each other, because yeah, you see one here. That's one of those guys. So that's a little bit of a bug. That's, yeah, this guy. That's not very fun, but yeah, that's, like I said, this is not a very, it's a very basic way of doing this. And of course you could do more sub-steps and things in order to get away with those things, because now we're just doing one collision detection and moving it accordingly. So if when it moves out of collision into another collision, we're fucked. And that could of course be taken into account. What we would need to do then is to take the sub-steps and make sure that the velocity and everything, or at least the advection or movement of the particles, is divided by the amount of sub-steps as well as the sourcing. But yeah, let's just see that the gravity kicks in. It should, right? It gets a lot. The small particles get a lot of speed upwards, and yeah, they don't seem to want to come down again. Let's just see if we add a lot of gravity, so it works. This gravity thing. Let's say gravity -0.1, and So they should fall down quite fast. Yeah, you see that they fall down eventually. And the cool thing, you could play around with density. You could do like one of the sources super dense or something like that, and just see that that works as well. So let's do the original particles, give them a density of 10 instead, and see what's happening. And as you can see, they just follow through while the other ones are just bouncing off completely. I think it's they tend to go past the other ones. So that is working as well. So yeah, we could also, just to make this, do a grid here and just copy the ground plane position, paste that into the grid, and paste relative reference, and just, oh fuck, sorry. Let's do it super big and merge them together. We should of course do this on object level, but what the fuck, who cares? So there we go. This grid is still not big enough. So there we go. There we have it. We can move that. And as you can see, they're bouncing off the grid. And now they're still super dense, so they just move along. Yeah, so this is basically it. I hope you enjoyed this. I think my next tutorial will be a little bit more useful than this, because like I said, it's good practice, but it's not something you take into production, because you could do this in a pop solver in like 2 minutes instead of spending an hour on it doing it this complicated way. But it works and it's quite fun. So yeah, thank you. Bye.